Hello, class. This is Mr. Hart, and this podcast I want to start on the first part of the pressure and fluids chapter. And this is probably my favorite chapter to teach in physics because we solve a lot of cool problems and go over some cool scenarios. So let's get started. Um, let's start with the question though. Why is floating ice important to life on Earth? Okay, think about that. What would happen if ice didn't float? Okay, well, if ice didn't float, it would sink to the bottom of the ocean and slowly build up over time until the ocean was pretty much just all ice. And so we wouldn't have very much ocean life and we'd run into a lot of problems. So it's really good that ice does float. But let's think about now, why does it float? What property of ice makes it float on water? Okay, and what it goes to is something you probably learned from a previous science class called density. Okay, so if ice is less dense than water, then it's going to float, which is the case. Okay. So we want to describe density mathematically. So if we look here, this is the equation. The density, which we represent with the Greek letter rho, it looks like a lowercase p, but this is actually the Greek letter rho. Okay, so the Greek letter rho equals mass over the volume. The density equals the mass over the volume. And how I always teach my students to remember this is I always teach them that density equals heart. Okay, so my name is Mr. Hart. But also when you draw a heart and you draw a line through it, okay, you get an M on top and a V on bottom. Okay, maybe that helps a little bit. Okay, you got an M on top and a V on bottom. So that's how I kind of always remember it: is density equals heart, and then you put the slash through, and there you go, mass over volume. Okay, so density equals mass over volume, or the amount of mass in a given volume. And so if you look at the units, they're going to be kilograms. Okay, masses in kilograms over meters cubed. Right, volume is meters cubed. Okay, so it's not that complicated. It's pretty simple. So you just take the mass and divide it by the volume. So let's try a simple problem. Okay, so the density of an object, the mass of 300 kilograms, a volume of 5 meters cubed. Okay, really simple. We just say density equals mass over volume. Okay, which in this case is going to be 300 kilograms over 5 meters cubed. Okay, and again, I apologize for the sloppy handwriting on the touchpad, but 300 kilograms over 5 meters cubed, which is going to give us 60 kilograms, 60 kilograms over meters cubed. Okay, so there you go. Simple enough. Just take the mass, divide by the volume. We got our density. Okay. If you are watching this podcast to make a participation, then try this problem. Okay, a cube of unknown material has has a mass of 12 kilograms and a height of 2 meters. What is the density of this cube? Okay, keep in mind it gives you the height, not the volume, so you'll have to find the volume of a cube given its height. Okay, but again, if you're making a participation, answer this question. All right, let's move on. Okay, so some vocabulary you should know. A fluid, okay, is a gas or liquid substance. So sometimes, or most of the time, people when we say fluid, they think of a liquid like water or juice or milk, right? Those are all fluids, okay, which is true. But we forget that gas counts as a fluid as well. So air counts as a fluid, okay, hydrogen, helium, any of the gases, oxygen, carbon, they all count as fluids as well. Okay, and this is important to note because when we talk about buoyancy, it's important to understand it counts for all fluids, all gases, all liquids. Okay, so you're going to want to know this word. Okay, and then also density, right? The amount of mass in a given volume. Okay. All right, so let us move on to buoyancy then, which is the ability of a fluid to apply a force, right? So you have a rubber ducky in a bathtub, right? The water is pushing on the rubber ducky. Okay, it is pushing up with a force, right? That water is applying a force to that object. That is buoyancy. Okay, and again, this counts for all fluids. So gases have buoyancy as well. Okay, so then we went and we did some simulations online with PhET. You can try these; they're pretty easy to show, or pretty easy to load and use, right? But what we saw is that the density is less than 1 kilogram per meter cubed, or sorry, 1 kilogram per liter, then the object's um, gonna float. If it's not, it's gonna sink, right? So if it's less dense than water, then it's gonna float. If it's more dense than water, it's gonna sink. Okay, that's kind of the basic idea behind density. Okay. All right, and then we did a lab. Okay, a homework lab where you had to find how the shape of an object affects the buoyancy. Okay. And then we talked about Archimedes' principle. Okay, so Archimedes' principle is an important principle. Archimedes discovered it when he was working for the king, and he's known for his famous, Eureka story, screaming Eureka through the streets after he had discovered buoyancy. Okay, so if you want to look up more about that story, it's an interesting story. But Archimedes' principle just says the buoyant force of an object is equal to the weight of the fluid displaced by the object. Okay, so how much water, for example, you displace when you jump in the bathtub is how much buoyant force that water is putting on you. So you can represent that with buoyant force equals the mass of the fluid displaced times gravity. Okay, the mass of the fluid displaced times gravity. Okay, so pretty simple to calculate. The problem with this version of the equation, though, is that it's hard to measure the mass of the fluid displaced. Okay, for example, if you put a boat in the ocean, you can't grab all the water that was displaced by that boat to determine how much force there is. Okay, it doesn't work out. Okay, so we need another way of viewing this for more practical situations. Okay, and it turns out we have another version we can use. Okay, and it's this version. The buoyant force equals the density of that fluid times the volume of the object that is in that fluid times the gravitational acceleration. Okay, so density of the fluid times volume times g. Okay. Now this is much more applicable because you can measure the volume of a object and you can find the density of a fluid. So you just need those two values to calculate the buoyant force. Okay, and a common density that people know is density of water. Okay, so a lot of people, or a common density you need to know is the density of water, which is 1,000 kilograms per meter cubed. Okay, so that's how dense water is. So if you have a cubic meter, a meter by a meter by a meter of water, it would weigh 1,000 kilograms, which is pretty dense if you think about it. Okay, so I just plug that into the equation. If it's in water, I find the volume of the object, times it by g. That's my buoyant force. Okay, so again, there's two different versions. Okay, it just depends on the question. In most practical situations, you're going to be using this version though. Okay, so let's try two problems really quick. Okay, so this one, it says an object displaces 3,000 kilograms of water when placed in the ocean. Was the buoyant force on the object? Okay, so this one, it gives us the mass of the fluid displaced. So in that case, we're going to want to use the first version. Okay, so we know it's 3,000 kilograms. Okay, and so we're going to plug it into the buoyant force equals mass of the fluid displaced times g. Okay, and again, I apologize for the sloppy handwriting. So mass of the fluid displaced times g. Okay, we know g, we know mf, so we just plug them in. So we say that's equal to 3,000 times 9.8, which equals, I think you're going to get, about 27,000, or not sure the exact number. I think it's actually 29,000. 29,000. Okay, so whatever 3,000 times 9.8 is, you're going to get that in newtons. Okay, so there's our buoyant force. That's the fluid displaced times g, which gives around 29,000 newtons. Okay, so again, if it gives us the mass of the fluid displaced, we use the first version. But in most practical situations, that's not what they're going to give us. So let's look at another example. Okay. So an object has a volume of 18 cubic meters and is placed in water. What would the buoyant force be on that object? Okay. So this case, they do give us the volume, right? That's easier to measure. So it's 18 cubic meters. Okay. and it says it's placed in water. And so we know the density of water, okay? The density of our fluid is going to be 1,000 kilograms per cubic meter, okay? So now we plug that into the second version of the equation. So the buoyant force equals density of the fluid times the volume times G. Let me rewrite that. Sorry. So density of the fluid times the volume times G. Okay, so we know the density of fluid, it's going to be 1,000. We know the volume, it's going to be 18. We know the gravitational acceleration is going to be 9.8. Okay, so we get 1,000 times 18 times 9.8. Okay, and I will calculate this one out really quick. So when you plug that into your calculator, you should get 176,400. Okay, and again, this is going to be in newtons. Okay, so hopefully you can see when you would use one version of the equation compared to the other. Again, in most practical cases, most real-world applications, you're going to be using the second version. Okay, but just know there are two different ways to calculate the buoyant force, but they will always give you the same number. Okay, all right. And so the last idea we want to cover is, why do we want to know the buoyant force? Why is it important? Okay, and it comes to this key concept, okay, that an object will float when the buoyant force is greater than the weight of the object, or the gravitational force. Okay, so when will it float? When the buoyant force is greater than gravitational force. So I calculate the buoyant force on an object using that equation, and then I calculate its weight, or measure its weight, its gravitational force. And if the buoyant force is greater, then it will float. If the buoyant force is less, then it will sink. Okay? And so in class we did the buoyant force lab to practice that, okay, and see that. Okay. But again, really important concept. Again, it just goes back to free body diagrams, right? If you had a box, okay, some object, and the force going down is less than the force going up, okay, you would expect that object to move up, right? And so that object will float, okay? So just simple Newtonian forces, right? But that's the idea. Buoyant force is greater than the gravitational force, then it's going to float, okay? So now we know how to calculate that, and now we can figure that out for any object. Okay, so hopefully that makes sense. Let me know if you have any questions, and thank you for watching.